So what I want to do today is I want to continue with viscous drag. I still seem to have an inability to write the word viscous drag effectively. V-I-S-C-O-U-S. There we go. Yesterday I solved the problem of viscous drag where the drag force was proportional to the velocity. You might say linear viscous drag. Today I'm going to solve the problem. I'm going to solve many problems today, but the first of which is viscous drag that is proportional to the square of the velocity. You might say, well, what is the true nature of viscous drag? The fact of the matter is, if I want to model viscous drag in any physical situation, I would write the viscous drag out as an infinite sum of terms, proportional, well, there would be a constant and then proportional to the square, constant and then linearly proportional to the square, proportional to the cube, proportional to the fourth power. This is just an approximation of what the drag force would be in any given physical situation. But it turns out, rule of thumb, I use a drag force that is proportional to the speed at low speeds. But at high velocity, like bullet velocity, we find experimentally that the drag force is more proportional to the square. So I'd like to solve that problem as well. So I'll proceed the same way that I did before. I have some object and it just suits me to continue to use a car. I guess it's a fast moving car at this point. But I have a car moving with initial velocity v0 exactly as I did in the previous lecture. Except now I'm going to have a drag force proportional to the square of the speed. So drawing my free body diagram, I have the weight mg directed downward, I have the normal force directed upward, and I have the drag force opposing that, where the nature of the drag force is proportional to the square of the speed. So I proceed the same way I did yesterday by writing Newton's second law, and indeed the way I proceed in all Newton's second law problems. It's really part of the training, and I know I'm harping on it, I understand that I consider the situation, draw the free body diagram, write Newton's second law, because that is where I get the equation of motion that describes the behavior of the system, and I use that to my advantage to derive some useful results in principle. So here I have Newton's second law: the sum of the force is equal to the mass times the acceleration is equal to the mass times dv dt. And so once again I have a relationship between the derivative of the velocity with respect to time and the velocity itself. The only change here is that it's the square. So the distinction here is really a mathematical one. I haven't had to do anything special in terms of Newton's second law. I just wrote an honest equation of motion, the differential equation that describes the behavior of the system. And now I need to get busy solving it. I hope that you'll recall in my last viscous drag problem that the way that I solved it was to solve for dt. Get dt alone on one side and then integrate. Exactly the same technique here, but you'll find that there's a twist as I go. So solving for dt, what's going to happen? Well, I'm going to have dt now on the left-hand side. I'm doing a few steps of algebra all at once because I think we're familiar with what's going on. dt is going to be equal to negative m over b, same as before, 1 over v squared, same as before, except the v squared, dv. And this is the integral, well, this is the equation that I have. And clearly the next step is to integrate both sides of the equation such that the integral of dt, which I made an argument is certainly just equal to t, it's equal to delta t, but if I select t0 be equal to 0, then it's just equal to t, has to be equal to, drawing constants out in front because they make no difference to the integral m over b, the integral of 1 over v squared dv. In our last derivation we saw some exponential functions crop up. It was quite fancy sort of physics and a little bit enjoyable to work with in my opinion. But that was all because I had in my integral 1 over v. And the integral of 1 over v is the natural log of v. And as soon as the natural log comes into it, that's where the exponential comes from. But look at this. I need to compute the integral of 1 over v squared. And that is not equal to the natural log of v. Can someone tell me, please, what is the integral of 1 over v squared? Can anybody say? Any one of our calculators? Negative 1 over v is absolutely correct. And so the result of this is negative 1 over v. But I have to evaluate that, and I should have put limits of integration here. I'm just going to do just like I did last time. The integral is performed from the initial velocity to some later final velocity. And so this is v0 here on my limits to v. That's how I'm performing that. So after I do the actual integration, of course, I've identified this before and said before, I'm not done. I have to do final minus initial to this. Notice that I have a negative sign inside the brackets and a negative sign outside. I'm content to eliminate those negative signs for the moment and have m over b, the inside evaluated at v, which is 1 over v, minus the thing evaluated at v naught, which is 1 over v naught. And so I've completed the calculus portion of it and that I've done the integration, but I have an equation very different from in the last derivation, but equivalent in the sense that I have t equal to some function of velocity. And that's not what I wanted. I wanted velocity as some function of t. And so what I'll do is make some effort algebraically to invert this equation. So let me start with t is equal to, I'm simply rewriting what I have down here. And of course, you probably realize I'm content to work higher on the board. No, you know what? I'm going to take an algebraic step. I'm going to take an algebraic step because why, rewrite things? I'm simply going to take this m over b here and multiply it to the other side so that I have b over m times t is equal to 1 over v minus 1 over v naught. I try to convince students because I know that when I do things like this, it seems like, well, you know exactly what you're doing and you go along. The fact is, I am, in a sense, making this up. Of course, from experience, I know what happens, but I am making this. You know the thing that's bothering me right now? The thing that's bothering me is that there's no negative sign out here in front of the b over m times t. It's bothering me that there's no negative sign there. I'm probably wrong about that. Everything's going fine. Everything's going fine because this negative sign canceled this negative sign. And this is the difference of this. Right? Yeah. So did I make an algebra mistake? It doesn't seem so. You agree that I didn't. I agree that I didn't. But I have a queasy feeling right here. I have a queasy feeling right now. And that happens, and what I could do is I could just go on and pretend like I don't have that queasy feeling, and then at the end you would never know that it happened. You'd be like, man, Charlie's so smart. He does all the problems, and he's so confident. I wish I was that confident. I'm not! You're going to have that queasy feeling, and what I'm suggesting to you now is what you do is you look back, when you get a little confused, you look back and look at your steps and say, have I done everything appropriately? And then if you feel that you have, just push forward and see what happens. Don't panic. Because when you try to invent adjustments to what you're doing, when you try to break the rules and think, oh, something different is happening, or I try to just plug a negative sign on there because I had a feeling it should be negative, so I did. Instincts are good, but in the middle of an algebraic machination like this, they can be really, really dangerous. So I'm going to go ahead and, ultimately everything's going to work out fine. So I want to get V0 by V by itself. V is what I'm solving for. So I'll add V0 over to the other side of the equation. So what I have is B over M times T plus 1 over V0 is equal to 1 over V. Now I have to invert it because I don't want V as a function. I don't want 1 over V as a function of T. I want V as a function of T. So to invert this, what I have to do is find a common denominator on this side and add the fractions. Well, the curious thing about that is this first part, b over mt, is not a fraction, so my common denominator obviously is just v0. So I'll multiply the numerator and the denominator by v0, and so what I get is v0b over m times t divided by v0 plus 1 over v0 is equal to 1 over v. So now I can combine those fractions, and what I have is 1 over v is equal to 1 plus v0b over m, and I took the privilege of changing the order of those terms just because I think it looks more attractive that way. It's purely an aesthetic choice. Divided by v0, and now I can invert it and get my final result. So my final result here is going to be that the velocity is a function of time, which again has no exponential function in it, is going to be v0 divided by 1 plus v0b over m times t. Now, does this have the dependence that I want? That is, does it behave appropriately? Because as I was going through the derivation, I said I got a little bit queasy about it. So let me check and see what happens. The way to check an answer, to see if it makes physical sense, is to consider how it behaves at the extremum. How does this thing behave at t is equal to 0? Does it give me the right result? Because I know that the initial velocity of the car is equal to 0, and so I checked. What does my expression for the velocity as a function of time say? Is the velocity of t is equal to 0. With t equals 0, of course, this is equal to 0, and the initial velocity is the initial velocity. Excellent. It's extraordinarily unlikely that I could have made a horrible algebra mistake and that still work out, right? So it gives me confidence that things are working out. What happens if t goes to infinity after an infinite amount of time has passed? Well, the denominator of this becomes infinite, which means this becomes infinitely small, which means the velocity diminishes asymptotically to 0. And if I make a graph of this function and I show it to you and I say, is this a 1 over t equation or is it exponential decay? You can't look at it and tell the difference between the two. You can't look at it and tell the difference between the two. It turns out that if you plot them on the same graph, 1 over t is a little bit extreme early on, right? But you can't immediately, looking at it, tell the difference because it has the same sort of asymptotic behavior. It starts at an initial value and it asymptotically approaches the time axis. As we go on, the velocity goes to 0. That is essential. What I could do now, and I'm not going to do, it's a funny thing they put in textbooks all the time, particularly advanced textbooks. You won't see this in your textbook. But in advanced textbooks, like when you're in graduate school, you'll see an author will write a thing and say, it is left to the student to show that this is true, because they just don't want to put it in the book and they feel like, you have to suffer as well. Now that I have that, you might consider, can I calculate from that the position and the acceleration as a function of time? I would find the acceleration as a function of time by taking the derivative of that velocity with respect to time, and then I would have the acceleration. I would find the position as a function of time by integrating that equation and then finding the position as a function of time. I'm not going to do that now. I'm going to move on to another more interesting idea, but that is certainly worth your time if you find yourself looking for some mathematics and some physics to do. So now I'm going to change it up a little bit and solve yet another viscous drag problem. So once again, same technique, same goal, to find the velocity as a function of time, but please consider now viscous drag when an object is falling under the influence of gravity. So I'm going to start here with an object that is subject to a weight, mg, that is directed downward, and so it falls. And when we do an introductory course in physics, of course we solve free fall problems. But when we do, we ignore the viscous drag. We assume that an object falls with an acceleration equal to 9.8 meters per second squared all the way. And so we do calculations as if they're realistic. But in those problems, we try to write those problems in such a way that objects don't fall very far. Because we know what happens. If you're a skydiver and you jump out of an airplane, in the first few seconds you accelerate significantly as the force of gravity pulls you towards the earth. But as you fall, the viscous drag of the air through which you fall increases, because as you fall, your velocity increases. And the viscous drag increases, until eventually the viscous drag force upward is equal to the weight downward. At such a point, you are in force equilibrium, and your acceleration becomes zero. This is known as terminal velocity, where you fall at constant speed. I haven't calculated it. We could do a quick calculation and find out what would your velocity be if you jumped out of an airplane and there was no viscous drag. Your velocity by the time you reach the surface of the earth would be spectacular. And there would be no parachute stopping you at that point. But of course, parachute wouldn't work anyway if there's no viscous drag. It's the whole principle of the thing. So viscous drag is important to falling objects, and also I might encounter an engineering situation where an object falls through a fluid. And falling through a fluid, it's certainly not free fall, but is instead falling under the influence of a viscous drag. So I'm going to include a viscous drag force upward here, and I'm going to say that drag force is negative BV. So once again, I'm looking at drag force linearly proportional to the velocity. Can you do this problem again and solve it with a v squared force? Yes, it is left to the student to do that as an exercise for themselves. Could you do this problem where that object is projected upward? In which case the viscous drag force and the force of gravity would be in the same direction. Yes, and it's left as an exercise to the student to do that, because we've certainly done enough of these at this point. When I'm done this, I'm ready to move on and do something else. There's plenty to do in physics that's entertaining. Before I get busy writing Newton's second law for this, though, I want to point out what happens in the situation where my velocity downward is sufficient, that the upward force of drag is equal to the weight force directed downward. When that happens, as just stated, that velocity, that special velocity where you're in force equilibrium, is known as the terminal velocity, Vt. That terminal velocity, put a negative sign there where I should not have, that terminal velocity multiplied by my drag coefficient here is equal to m times g. And so I can calculate immediately, without any fancy calculus or anything, what the terminal velocity would be. It's simply mg divided by b. And so now I can calculate what the ultimate velocity will be in free fall. So now I'm going to continue on doing things the Newton's second law way. Notice that I wrote the BV upward as a negative force. Since the object is falling downward, I'm going to operate contrary to what I say on a regular basis in lower level physics classes. I'm going to choose downward to be the positive direction. It's just algebraically convenient for me here. So when I write Newton's second law for the purposes of getting my differential equation that describes this falling motion, the sum of the forces is equal to the mass times the acceleration is equal to the derivative of the velocity with respect to time. Now, that means that negative BV plus mg is equal, oh geez, do you see what I did there? Oh my goodness, my goodness. Yeah, well, that's going to happen, and when that happens, you have to call me out on it. You can't let that sort of thing just stay there. I left the M out of Newton's second law. You know, who needs inertia? But if there's no inertia, who needs force? Well, there you have it. Is equal to m dv dt. I think that an instinct that all undergraduate students sort of develop is to know when things are getting messy. This is not so nice an equation as the one that I had before. Anytime there are additional terms in an equation, you have an instinct that tells you this is going to be a mess. It is going to be a little sloppier than I would hope for, but you know, it's all going to work out okay. I just sound ridiculous saying that. Negative b over m, I'm going to divide through by the m. And look at that negative b over m appearing there. I see these sorts of patterns happening in my physics as I go on. The negative b over m, it's been all over the place in viscous drag. And so if I find myself out in the middle of nowhere, writing on a blank piece of paper, and I see the b over m's appear, it'll give me a little bit of confidence that something's going right, because that tends to happen. Sometimes on our exam, what they'll do is instead of a b, they'll use a k. And I suppose that is to make sure that you're not memorizing the answers to things. So they'll throw in a K or an alpha or a beta or something to make sure that that you understand as opposed to simply memorizing. So dividing mg, I get g there, and then on this side I'll simply have dv dt, which I think is why I didn't include it. I think I was a couple steps ahead on the algebra. So there it is. Now I've got that pesky g hanging in. If it wasn't for the g, this would just be the first viscous drag essential that I had done. So then I look at this and well, what am I going to do? Well, it turns out, lucky you, the strategy is exactly the same for solving this. Strategy is exactly the same. I'm going to solve for dt, and I'm going to get everything that's v on the other side of the equation, because the equation is still separable. The equation is still separable because dt is going to be equal to 1 over, I guess I'll write it g minus b over mv dv. And so proceeding as I have done, solving for t is equal to, integrating to get t. That's what's happening here is I'm thinking ahead in my equation. I wonder if I'm bored. The integral of dt, that's a nice integral sign. This marker, well, this marker's a little thick. The integral of dt is equal to t is equal to the integral of 1 over g minus b over m v dv. And with little calculus experience, you might look at that and say, I don't know how to solve that integral, because I look at my integral equation sheet and I go down and I don't see anything that matches that. I can't solve it because there's a problem. What's the problem? Well, you are the problem, this gobbledygook in the denominator, and so I'll say let u be equal to g minus b over mv. You see, the physics is not more sophisticated. The mathematical technique required to solve it is more sophisticated, but not the physics itself. Once I select u, I'm immediately going to do du dv. I'm immediately going to calculate that derivative. Well, g is a constant with respect to v, so that just goes away. And v to the first power becomes v to the 0 is gone, so this just becomes negative b over m. Because I've calculated du dv, I can solve for dv and find that dv is equal to negative m over b du. So I can make that substitution into my equation, my integral, so that I have t is equal to the integral. By the way, there's a calculus thing they do here that some of you might be thinking about, that when you do a u substitution, you change the limits of the integration to match the u substitution, and then after you substitute back, you change the limits again. There's no reason to do that. I'm going to leave the limits out of it until I've got a handle on what I'm doing here, and then I'll talk about the limits, and it's perfectly safe to do so. But anyway, if I make the substitution that dv is negative m over b du, then this becomes negative m over b. I would prefer that I'd taken those constants out, but that's okay. 1 over u du. So my integral, that was unsolvable before, has become 1 over u du. I now know how to solve that integral, because the integral of 1 over u is du is going to be the natural log of u. So what I have here is that the time is equal to the integral, no, not the integral, I just performed the integral. I'm just enjoying writing integral signs like that. That's kind of a nice one, oh well. Negative m over b times the natural log of u, but u is g minus b over mv. Be careful. When I complete my integral, I'm not done, because I have to consider the limits of integration. Now here I have options for how my solution turns out. I've been emphasizing recently more than ever that when I first start the problem, I should consider completely what's going on before I proceed. And I didn't exactly do that here. I have a question. Is it dropped from rest and falls? or do I throw it downward with an initial velocity? Of course, the most general thing to do is to throw it downward with an initial velocity. I don't feel like it. So I'm going to state as part of the problem description that it is dropped from rest. I can easily go through and do this with initial velocity. It makes very little difference. It just makes the equations a little bit more busy. So what are my limits of integration? Well, from 0 to whatever the final velocity is. Charlie, don't you mean to the terminal velocity? No, I don't want to go all the way to the extreme, because I want to know the velocity at every instant in time. So my final limit is the velocity sometime later. So they'll be able to solve that out in the end. Well, now I have a little bit of work to do, because I have to do this limits, which is like doing the final minus initial of the thing. And so I'm going to get the difference of two natural logs. The natural log evaluated at v, which is just g minus b over m times v, minus the natural log evaluated at v is equal to 0. Well, that makes this part 0, but look what happens. That g still survives, the natural log of g. In our first viscous drag derivation, we had asked for a rule of the difference of natural logs. The difference of natural logs is the ratio. And so here I have the time is equal to negative m over b times, well, I don't need the brackets anymore, the natural log of a rather complicated thing, g minus b over m times v divided by g. And what a hot mess that is. It is. Here I have t as a function of v, and that's not what I want. I want v as a function of t. Two things. It'll be okay. It's not as bad as it seems, and this is going to happen many times to us now in our physics, so we better get used to it. This is doing physics. I want to get the natural log all by itself, so I'm going to take the b over m to the other side, and what I get is negative b over mt, which I'm so glad for, because that's familiar to me, isn't it? Negative b over mt. That's very familiar, because it shows up in my viscous drag. So I'm confident things are going well. And then over here I have, once again, the natural log of g minus b over m times t divided by g. And so what I'm going to do is exponentiate both sides of the equation. I'm going to exponentiate both sides of the equation. When I do, I get e to the minus b over mt, which is very satisfying, is equal to g minus b over m times t divided by g. Oh, I lost my, hang on. Huh? Where? Oh, I put t's instead of, okay, thank you. Did I say t? Because I had a b over mt on the other side is why I was saying b over mb, and it's all good. It's all perfectly lovely. I'm going to, obviously, in order to solve for v, I got to get this g up on this side. So I'm going to multiply both sides by g, which will cancel a g down there, and put a g up here. I apologize, but of course I'm running out of space there for doing that cancellation. So then, what do I have? I'm going to add b over mv to this side of the equation. I'm pausing for a moment, because once again I have that uneasy feeling, but it may be inappropriate. Oh, it's absolutely fine. It's perfect. Okay, see what happens? You just got to be patient. Don't freak out. Everything's going to be okay. So, with the limited space that I have left, I'm going to have to do something ugly and go up into the far corner of the board there. I apologize. But what I'm going to get here when I spin this thing around is b over m times v is equal to g minus g e to the minus b over m times t. And that's horrible. But what I'm going to do is on the right-hand side of this equation, I'm going to factor the g out. And then I'm going to take this b over m that's on the left-hand side, I'm going to multiply it over to the other side and get my final result. My final result is that the velocity is equal to mg over b times the quantity 1 minus e to the minus b over m times t. Wow. Isn't that just picture perfect? Look at how splendid it is. The coefficient out in front is mg over b, which I know is the terminal velocity. So where's this thing going? Terminal velocity. And sitting next to the terminal velocity is my very dear friend, 1 minus e to the minus x. That functional form that I know how it behaves. What is this thing doing as a function of time? Well, let's make a graph of it. The velocity of the thing as a function of time is going to go like this. And the asymptote is the terminal velocity, mg, divided by b. It does exactly what you expect. The velocity starts at 0, and then it exponentially approaches. not exponentially approaches, but it approaches in an exponential sort of way, in a natural way. The terminal velocity, asymptotically approaching. See, the attitude there is wrong. Want to do this one. Can't wait until class is over so I can go somewhere in a quiet place and slap down a piece of paper and bust that out. Fantastic. Good times. Makes you feel good.
So the answer to that one